Let's get the slideshow set up. From current slide. We'll go from here. Okay, before we get started today, let me just go over a couple of more things, other things. Okay, I believe I told you early in the term that there was a meeting coming up that I had requested that we go to Atlanta at Spelman College because the meeting there was Friday and Saturday. It wouldn't interfere with classes. The vice president wanted to do it Monday and Tuesday in New Orleans because he didn't want to mess with the weekend. So instructors worry about classes, administrators worry about weekends, I guess. And also that was going to be further, going to cost more. I cannot see why we requested that, but we did. I found out today we did, well, I found out earlier we did get that, but now it has been approved. I've got to do my travel for it. I just don't remember what Monday it is. I don't believe it's next Monday. It's the one after that, I believe. So that means sometime we're going to try to have to make up that class. And about the only time I can is a Tuesday or Thursday afternoon or morning. 10 o'clock I could do it. Now that would just be the class part. To do class and lab, we'd have to do it on a Tuesday or Thursday afternoon. So if y'all can make it on a Tuesday, Thursday afternoon, anybody, then I'll do it with, I'd rather have somebody here so I can bounce, see if I'm going too fast, too slow, or whatever. But if I'm not, I'm just going to have to make it up by myself, and that's really boring. But if anyone can come, please let me know. We'll talk about it more next time. Okay, that's one thing. Number two, I think I told you last time, they did agree finally to pay me for at least one overload course, which means I have to extend my office hours. So I've done that on the syllabus and on my locator card, and I got those put on Blackboard. Okay, basically I was ending my day on Tuesday, Thursday at 3:30. Now I go to 5:15, or later if I need to. Like if I make up this class, it will be later than 5:15. But that is what we're doing. All right, there's that. One other thing. I got everything that's been turned in from this class graded. My next class, I got almost all of theirs graded, but I don't have it on Blackboard yet because yesterday I had to take care of getting all those syllabi changed in my locator card and all that stuff, and that ate up way more time than it should have, but it did. So hopefully tomorrow, I've got to get my travel arrangements made. That's going to eat up some time, but after that, hopefully I can get the rest of the grading done and the grades put on Blackboard. If not, I'll try to do some of that Friday, because Friday I've got an infusion, so I'm going to be stuck in a chair, and literally stuck in a chair. Never mind, that's bad pun. And so I will be have some time before the Benadryl kicks in that I can do some catch-up. So I will be doing some of that on Friday. Because there's time between the labs and the infusion, so I will have some time to do it. Okay, but sorry I don't have it done yet. I had not planned to get behind on getting Blackboard done this early in the term, but just everything's happening, it seems like now. First, any questions for anything we've done so far? I don't recall seeing anybody here today that was not here last time, so all of you did get a copy of the lab, right? And you all got a copy of the first test, right? Okay, good. You can turn that first test into me anytime you finish it. Technically, the due date was next Monday, but like I said, the woman who called on the phone won't be able to pick hers up until next Monday. So obviously, if I give her some extra time, which I have to, then you can have time if you want to. But if you get it finished, go and turn it in. Okay. No questions? Okay, we were talking about accelerations. We got this far, and in our text, this is section still in 2.1. They just break up the sections differently. In the text, they do 2.1.1, 2.2, 2.1.2, and 2.1.2.3. On the slides, they did 2.1, 2.2, and 2.3. So those numbers will be off a little bit, but you see where it is in the text. All right, instantaneous acceleration. Very similar to what it was with instantaneous velocity. Average velocity was the slope of the secant line between the initial point, final point, change of displacement over change of time. Instantaneous, not the slope of the secant line, but the slope of the tangent line. That says that delta t is approaching 0. What is the delta x or delta s or whatever over delta t? Same thing with acceleration. Average acceleration is change of velocity over change of time. Okay? Instantaneous acceleration is that change of velocity over change of time as that time interval gets smaller and smaller and smaller. So it's not the slope of a secant line between 2 points. It's the slope of the tangent line at a single point. Okay? That's what instantaneous acceleration is. The limit of the average acceleration as the time interval goes closer and closer to 0. When the instantaneous accelerations are always the same, that means the acceleration will be uniform. In other words, for any different time interval you choose or any different point you choose, if the acceleration is always the same, then we say the acceleration is uniform. The instantaneous acceleration will, I think that's supposed to be always, not will all be, but will always be equal to the average acceleration if you have uniform acceleration. Okay? In other words, another word for uniform, constant. If the instantaneous accelerations are always the same, that means you have a constant acceleration. They never vary. So uniform and constant. In this context, they mean the same. Any questions on that? By the way, let's see what the next slide says. Okay. No. Okay. In your text, they point out to you the unit, the SI unit for acceleration is, and I think we had this for average too, is change of velocity. Velocity is SI unit. What would that be? Meters per second divided by second. Meter per second, also known as meter per second squared. Okay? There's no such thing as a square second, so that's what they mean by second squared, per second per second. Okay. Average acceleration is the slope, I just said this, of the line connecting initial point and final point. Average acceleration would be the acceleration between those 2 points. Okay? Finite delta t, finite delta v, the slope of that. Okay? If you plot the velocity on the vertical axis, time on the horizontal axis, plot those velocities, pick 2 points, and the slope of that line will be your average acceleration. The instantaneous acceleration is the slope of the tangent line at whatever point you're interested. The line tangent to that velocity versus time curve, that's going to be your instantaneous acceleration. Just like it was for velocities, average velocity is the slope of a secant line, instantaneous velocity, slope of the tangent line at the point where you're interested. Okay. All right. This is figure 2.9b in your book. They didn't show 2.9a, which basically is car going from one point to another point. At the initial point, you have some initial velocity. Sometime later, you have a different velocity. So your average acceleration would be your change of velocity over that interval divided by the change of time over that interval, which basically is the slope of that secant line, the blue line there. The actual path is the red, okay? You can't do that with average velocity, but we can average acceleration, okay? The slope of the blue line connecting P and Q, the average acceleration over that time period, delta t, E final minus the initial. Now, were to draw a tangent line at P, the slope of that line would be your instantaneous acceleration at P, because it's a velocity versus time graph. At Q, there's a tangent line. It's actually slowing down. P to Q is accelerated on average between there, but by the time you got to Q, you passed your maximum velocity and now begun to slow down or reduce that velocity. So now you have a negative acceleration. Instantaneous at a fixed point, average between 2 points. Okay. Sorry, I was cramming down a salad before class and I've got some stuck between my teeth and it's really irritating me. Okay. All right, before we get to that slide, there is a quick quiz. Okay? Okay. Yuck, it's going to be so hard to do this. How many of you have books? Quite a few. Can you look on with someone, if you don't have a book, can you look on with someone who does? Just temporarily. And here is Larry, right? Okay. Good deal. All right, I was just saying, if you have a book, if it's this edition, these figures are on page 40. Quick quiz 2.3. So if you don't have a book, see if you can look on with someone who does. Okay? If not, you can probably wing it. Okay. In your text, you'll notice the A graph there, the little A in the green background, represents a graph of velocity of different objects moving in a straight line as a function of time. Velocity versus time. A, B, and C are all velocities versus time. Okay? The possible accelerations of each of those objects as a function of time is shown in D, E, and F, but they're not necessarily matched up properly. Okay? So the question here is to match each velocity versus time graph with an acceleration versus time graph that best describes the motion. Okay? Now, I'm going to do very quick graphs here for those who don't have one, have a book. Okay, here's your A. It's basically something like this. This is velocity versus time. B is, this is A. B is like that. And again, velocity versus time. C is bizarre. Okay, no, okay. It's okay. Now, I want you to tell me what the acceleration versus time graph is going to look like for A. Anyone want to hazard a guess? If you got a book, you can look at D, E, and F and guess which one of those it might be. What would the acceleration look like? Okay, how do we define acceleration? Change of velocity per change of time. Here's your change of velocity. From here to here would be there. Change of time would be that. Same change of velocity here, same change of time there. Same change of velocity here, same change of time there. Guess what? What's the slope of that line? A fixed number. The slope is not changing, is it? So therefore, what will the graph of the acceleration look like? slanted, it is E. I don't have room to draw them all. That's why I'm asking you to do this. The acceleration versus time is going to be a constant. That shouldn't be slanted down. It's a constant. Okay? Horizontal line. What kind of acceleration do we call that? Just gave you two words on the previous slide that meant the same thing. They gave you one, I told you the other. Okay? There's the previous slide. No, it isn't. Here, there's two slides earlier. When the instantaneous accelerations are always the same, the acceleration will be uniform. And this, the acceleration is always the same on this one because the slope of the velocity versus time is constant. Okay? So that's uniform acceleration. That would be E. Okay? Now, how about the V curve here? This is velocity versus time. What does that acceleration look like? Okay. A little bit of a hint here. If I had drawn that well, the slope down here at the very bottom is horizontal slope. What's a horizontal line? What's the slope? 0. So it better start with 0. Okay? Then it gradually increases, so the acceleration is increasing all the time. What would that graph look like? What would that graph look like? Gradually increasing the entire time. That would be your, did someone say D? You're absolutely right. B matches with this. This is a parabola starting slow, starting at 0, 0 slope here. The slope, meaning the acceleration, is gradually getting greater and greater and greater with time, starting at 0 and going greater and greater and greater with time. So that would be this slope. All right, then it's real hard to figure out which one C is, isn't it? Okay, let's see if that makes sense. Without showing it, you tell me which it is. What can you tell me about the acceleration here? This is the velocity versus time. What can you tell about the acceleration there? Just like this one, right? What would that be? This is the velocity versus time. What would the acceleration be? What was the acceleration for this one? Constant. So this starts out constant. Okay? So it starts out constant. Some value, not 0, because it has some slope. What's happening to the velocity here? Okay. Hang on to that thought until I get it. What's your name, please? Amber. Okay, Amber. Okay. No, you're in here. There you are. Okay, has anyone else come in since the call roll? Okay. What can you tell me about velocity here? This is velocity versus time. What can you tell me about velocity here? Constant. So what's the acceleration? Not changing velocity. The change in velocity is 0. So this one starts off at a constant acceleration and then precipitously drops to 0. So that's why F is the answer for C. Does that make sense? All right, good deal. And hopefully in the back for quick quiz 3, if I can find it quickly, which I'm having my doubts now. Ah, here we go. Quick quiz 3, velocity versus time. A has a constant slope indicating, so that would be E. We got that one right. Graph B is D. Yep, we got that right. And graph C would then be F. Good deal. Example 2.3 is catching a fly ball. Do any of you feel like you need to see that one? So I can do it. Just let me know. Yay or nay? Move on or not? Huh? Don't move on? Or move on? Move on. Okay. There's an organization called that, isn't it? Okay. Never mind. Okay. In our book, it's 2.2. On the slide, it says 2.4, but this is it. These are our motion diagrams. Okay? Velocity and acceleration are sometimes confused with each other. Don't. Okay? But they're very different concepts as illustrated by the help of motion diagrams. Okay, now what a motion diagram is something like this. Just imagine that your object is there doing whatever it's doing in perfect blackness. And you have a camera that you keep the aperture open the whole time. But it's totally dark, so nothing's happening. But then you have a strobe light that flashes at a very fixed rate. So you see on the film where the car was from the first flash, and then the next flash, and the next flash, and the next flash. So in other words, this is the same car, same road, but at just different times because the flashes come at different times. So what can you tell me about the velocity of this car? It flashes at given intervals, and so its displacement is the same for every interval. What would that make the velocity? Constant. What would that make the acceleration? 0. Exactly, because it's not changing velocity. So this car moves at constant velocity, which would be 0 acceleration. So we could call that uniform velocity, meaning constant velocity. Shown by the red arrows, they don't change lengths. The cars are spaced evenly. It's the same car just taken several times, maintaining the same magnitude of that velocity. Because the velocity is a fixed amount, but always constant, the acceleration is 0. Because there's no change of velocity between that one and this one or any of them. The acceleration is 0. Now that's also uniform. It's just the constant is 0. Okay. Usually we mean constant being non-zero, but that is indeed uniform. Okay. How about this one? What can you tell me here? Now, first, this is the picture of the car. What can you tell me about displacement? Small, larger, larger, larger. So the displacement is increasing over time. What does that tell you about velocity? Change of displacement over change of time. This one's short, a little longer, a little longer, a little longer. Not much difference between these, but just a little bit. Okay? What can that tell you about acceleration? This is an increasing velocity. Now you don't know for sure if it's constant, but it sure looks pretty close to it. The acceleration does appear to be uniform. So this car has a constant acceleration because the velocity is changing by about the same amount every one, and has a constant acceleration in the direction of its velocity, so therefore the speed is increasing. So velocity and acceleration are in the same direction. Acceleration is uniform, meaning it's constant. Okay, the violet arrows, that's not violent, but violet arrows maintain about the same length, and the velocity is increasing, but by about the same amount every time. Red arrows are getting longer. The positive velocity and positive acceleration, because they're both pointing in the plus direction. Remember, they are vector quantities, and since we've got one-dimensional motion, all we're using for direction is plus or minus. So those are both plus. Does that make sense? Okay. All right. Here's another situation. What's happening here? Let's first deal with displacement. Big, less, less, even less. Displacement is decreasing over time. What does that tell you about velocity? The displacement is still in the same direction. Velocity is in the positive direction, but getting smaller and smaller. Big here, smaller here, smaller. Because a big velocity is going to go further. With a smaller velocity, it's not going to go as far. So it's getting less over time. What does that tell you about acceleration? Change of velocity here from small to bigger. Small number minus big number is a negative number over the same time interval. And as long as that difference is the same each time over the same time interval, the acceleration is constant, would that be uniform? Is that uniform acceleration? Yes, because it's constant, even though it's in the opposite direction, okay? So the velocity is decreasing as you go to the right. In other words, the velocity is getting less, so that means the acceleration is a negative acceleration, but it appears to be constant negative acceleration. This car has a constant acceleration in the direction opposite its velocity. Negative acceleration, positive velocity. Doesn't look like it's going to stay positive for long. It's approaching zero. The acceleration and velocity are in opposite directions. The acceleration is uniform, meaning it is constant. Violet arrows maintain the same length and direction. The velocity is decreasing. Red arrows are getting shorter. Velocity is positive, but the acceleration is negative. Make sense? These are called your motion diagrams. Okay. Oh, some more of these. Oh, this is the same three just done over again. Summary. They just did the same three in the same, all on one slide, whereas before they did it on 3 slides. Makes a lot of sense, doesn't it? Okay. Any questions on those? Okay. Now, a big boo hiss here. They're moving into 2.5, which is one-dimensional motion with constant acceleration. We're going to talk about the motion, the kinematic equations. Okay, that's what these are. In your text, however, they don't have these quick quizzes on the slide just like the last one. In your text, you have some, these are for the quick quiz. Your A, B, and C, boy. Okay, the top of the page toward the right, where A, B, and C are horizontal there. If you don't have a book, try to look on with someone who does. Okay? These are displacement curves. Okay, I'm going to draw them here again because this is the only slide I have that has a lot of white space. The old package that I used to use had just some white pages I could pull up anytime I want to. This new improved cheap package, doesn't. Okay. Here is your graph A. This is displacement over time. And since it's one-dimensional motion, we'll call displacement in the x direction. You could do it any variable you want to there, not B or A, that would represent velocity. So here's what we've got to begin with. Okay, that's your A. Here's your B, something like that. And here's your C. Something like that. That's not very good representation. Okay. These three graphs represent position versus time. X via t, x via t, x via t versus t. All right. For objects moving along the x-axis, which, if any of these graphs, is not physically possible? Or are they all possible? Which of these are not physically possible, or are they all possible? Help me, help me. What you think? Just tell me you think, okay? Any of these not physically possible? Or are they all physically possible? This one right here? Why isn't that possible? Okay. You're kind of right. Well, this indicates that this time t, you're at this position. This time t, you're at that position. All so far on the x-axis. This time you're at this position. This time you're at this position. All this is fine. This time you're at this position. This time you're at this position. But at this, wait a minute. At this time, where are you? Are you here or are you there? You can't be in two places at once. And this says that you're going backward in time. You can't do that. Time only goes forward. So this is not possible. Back in math class, you would say, this is not a function. It fails the vertical line test. Not possible. Okay? The other two are perfectly fine. Okay? So that's 2.4. Should be, next page, right here. B. B was the one not possible. All right. This is going to be really hard to do, but let's try it. Okay. 2.5 says in figure 214A, for those who have books, that's the thing at the very top left corner that has the little dots. You see that? That's 214A. Diagram of a multi-flash image of an air puck moving to the right on a horizontal surface. The images sketched are separated by equal time intervals. So those little gray lines are each an equal time interval. Okay? The first and last images show the puck at rest. Okay? So let me try to do this. This is A, and this is just showing from okay, 1, 2, 3, 4, 5, 6. These are our time intervals. They're supposed to be equal, but forget that. Okay. That means the puck is at rest. It's not moving, even though it does seem to be a little bit further along. You just can't see them stacked up. And here they are at rest again. Okay? You got a puck here. It's a closed puck. A puck here. A puck here. A puck here. Oh. I didn't get enough spaces there. Sorry about it. Okay, let me just put one in there. Sorry. They're supposed to be equal length. They're not. Okay. Here, and then you got three together. Okay. Just imagine those are all the same length. Okay. Yeah. Okay. Figure, the A part of this says a figure 214b, and please look at a book. To draw these is really messy. Which color graph best shows the puck's position as a function of time? Okay. Okay. Position as a function of time. Well, if that's at rest, its position is, let's just say, the first two times it's right there at the origin, not moving. Well, they all start out that way. That's fine, right? Then it moves up just a little bit to here. Now, this is x versus t. Okay? X versus t. Okay. Because the dots are all moving in that direction, we can't tell any of them backed up and came back. Anything that does this can't be true. That's always got to be strictly increasing because all the pucks are, except maybe at the very end and the very beginning. Okay? So if you look at that B one, the red line shows you've been somewhere and come back. That one can't be true. Okay? The green line looks like there's hardly any motion at all until you get to the very end, and then you have a sudden motion. That doesn't look good. So I would say it's the bluish purplish line that is fairly uniform in doing. It started here, it went up a little ways, then a little ways more. In fact, it stayed almost the same. It almost seems like there. I mean, it's still moving forward, but it went at the same slope. Then it increased a little bit, and a little bit more, and a little bit more, and then it's hard to say what's happening in the thing because those are stacked on top of each other. So that's the one that's closest to describing what we've got. It's almost, not quite, but almost a steady straight line. Okay? So that one has to be the blue line. Okay. Now, in figure 214C, which color graph best shows the puck's velocity as a function of time? Okay? And this would then be a V versus T. Now, you look at that, the velocity starts out not huge. Okay, it starts out pretty slow because it's 0 for a while. This is v versus t now. 0 for the first time, but then it increases and looks to be fairly constant for the next time interval, but then increases a little bit more, and a little bit more, and a little bit more, and then slows to a stop. So it goes to 0. So that would be, if you look at that, again, it looks like the blue line is going to be your best bet there. Okay? Then figure 214D, which color graph best shows the flux acceleration as a function of time. Well, acceleration is the slope of the velocity curve. Okay? And the slope of the velocity curve seems like to me would be slightly positive to begin with. It's so hard to describe and so hard, even harder to draw. Take your book, read through it. If you don't have a book, I feel like we're wasting time almost to do it. That one's a bit tough. Let me just give you what they say. 4 was B, was impossible when we got that right. Blue graph, red graph, green graph, okay? And I said blue for the middle, but I was doubting on the blue. But it's just really hard, especially with my drawing. So let's move on to 2.4. I mean, it's 2.3 in the text, and it's 2.5, I think, here. Okay. So we're looking at one-dimensional motion, especially, okay, with constant acceleration. What's another word for constant acceleration? Uniform acceleration. Very good. Now, these equations are used in situations for uniform acceleration. They do a little bit better job in the text of explaining where these come from. So let me try to fill in the gap a little bit. That first equation basically comes from here. What was our definition for acceleration? Does anyone recall? Pretty simple definition. Change in velocity per change in time, right? That's acceleration. Okay? Now, tell me what delta means. V final minus V initial over T final minus T initial. Okay, now we're going to do something a little different with time. Since time is sort of a fixed quantity, it doesn't vary, we're just going to use T to represent a time interval. We're just going to assume those time intervals are just whatever they are. You know, the earlier things we're assuming they were constant, that's fine. So that's what we're going to replace by T, just T, and that's going to mean time interval. Well, let's lose the final, and this will be any time, any velocity final. And now the book, for some reason, goes from initial to original, VO. So that's going to change. This just is going to become T. Multiply both sides of the equation by T. You lose the T here, you get AT. Add to both sides of the equation V0, and that gives you V is equal to V0 plus AT. So that's how we get this one. It basically comes straight from our definition of the acceleration. V minus, this is V final, V initial. You just say this is V, this is the original V. But that's your function, your equation. Now, almost similar to that was take that first thing, now let the change of velocity just be V, and multiply both sides of the equation. I'm sorry, this goes back to X. Now we do our definition of velocity. Average velocity was change of X over change of time, right? So we're just going to make this time, okay? And this would be multiply both sides of the equation by T, and you get delta X is equal to average velocity times change of time, or just T, okay, time interval, okay? So that gives you exactly this one. Change of velocity is average velocity times time. But as long as you got constant acceleration, then your average velocity is not just the change of X over change of time, it is also, since you've got constant acceleration, it's your initial velocity plus any other velocity divided by 2. Average, just like your average 2 scores. So we can change this average velocity only when you have constant or uniform acceleration. Change that to the sum of 2 velocities, any 2 velocities divided by 2. And then that gives you time. So that, this, and this are the same as multiplied by time. Okay? Now this one takes a bit more description for us, so I'm just going to give it to you. If you have just about all I can say is you just about have to remember this one. Okay? Remember, this A is a constant now. Uniform acceleration means constant acceleration. Okay? Your change of displacement, this is your change because of your initial velocity, because that always changes if you have any velocity going on there, times T, plus how much your velocity is changing with acceleration, and that basically is tied in with that, 1/2 AT squared. So basically what I would say, think of this is distance over time times time, that gives you distance. This is distance over time squared, so you have to multiply it by time times time squared, to get this answer as well. So just remember that acceleration requires the time squared, velocity just requires the time. Those give you distances. Now, here's just a little hint. When you have these formulas, now this won't absolutely always be the case, but it will most of the time. When you have a formula and you have a variable raised to the second power, expect to have a coefficient with 2 in the denominator. Just a couple of problems we'll have in the text that will not meet that, but just about all the rest of them will. If you have a duplex in the numerator, then you have a 2 as an exponent of your variable, then you're almost always going to have 2 as a fractional form, 1 over 2. Okay. Now, if you follow what they do in the book, you'll see they take this form and a form that is sort of like this one and try to mix them together to come up with another form, and this is basically what you come up with. V squared is equal to V naught squared plus 2a times delta x. And again, it's using some of this. If you solve this equation for t and combined it with this one, put the t in for that, you almost come out with this one. It's pretty close. Let's look at the unit side. This would be, say, in meters per second. Meters per second. So far, so good. This is meters per second squared times meters. So this would be meters squared per second squared. Meters times meters, meters squared per second squared. This is meters squared per second squared. This is meters squared. So the units work out. Where did this t come from? 2 come from? Basically multiplying the right place to put it. You can't get to it exactly here. I was trying to think of an easy way to remember it. There really isn't. Basically, go back and use these formulas. You'll use them over and over and over and over again. Now here's something I want to point out to you, and this will be important in problem solving. Notice what we've got here. Time, accelerations, and velocities. What are we missing? X. No displacements here. So if you have a problem that has nothing to do with displacement, but either gives you or you're looking for one of these variables here. Now this is a constant actually. This actually also is a constant. But then this would be they either give you the time or the velocity, or you one or the other. Then you can use this formula, but you're not interested in displacement. Now notice on this one, you have x, v, t, v, t's. You don't have any acceleration in this one. So if your problem is not dealing in any way with acceleration, and you're given either 2 of the 3 or something to relate them together, then this is the one you use. You use the formula that matches what your data are. Not just what the data are, but also what you're looking for. What have we got and what are we missing here? We've got x, time, acceleration. We don't have velocity. Not final velocity. We have initial, but that's just a constant. Okay? What are we missing here? We've got velocity, acceleration, and displacement. What are we missing? Time. So you see each one of these has 3 out of the 4 quantities. You have time, displacement, acceleration, and velocity. This is missing displacement. This is missing acceleration. This is missing velocity, final velocity, and this is missing time. So if your formula, if the data you're given gives you all but one of these, or also the thing you're looking for, you have to include that, then you use the formula that fits best. Okay? Now they do a bit better job of deriving these in some senses, or at least giving some sort of credence to it, you know, kind of how they got there, okay? And if you follow those formulas, these that you see here are listed as, the top one's 2.6, the next one, well, they don't show as 2.7. 2.8 is the second one here, 2.9 is the third one here, and 2.10 is the last one there. They show some others in between that they don't show here, but that's how you get them. So, trying to find exactly. All right. The old slides in the new book aren't meshing extraordinarily well, but that V average that you see on your page 43, 2.7 basically shows up here. V average here is equal to this thing there. And there you see it exactly the same in your book. They just phrase it in a form here a little bit different. This gives displacement as a function of velocity and time. You use this when you don't know and aren't asked for acceleration. That's when you use this one. You don't know, in other words, I haven't given it for you, nor are you asked to calculate acceleration, then you use this formula. Okay? This one, it shows velocity as a function of acceleration and time. What you're missing is the displacement. So use this one if you don't know the displacement and you're not asked to find the displacement, but you're given 2 out of 3 or 3 out of 4 of those pieces of information. Okay? Again, just because you're given V null, you're not necessarily given these, so you might have to approach that a couple ways. This is FA, right? All right. Still missing Nick, Raven, Charity, Darius, Rhea. Right? All right. So this is repeating some of the stuff I've already said, but it's phrasing it maybe a little neater. So I'll go this way. Now this is your graphical interpretation of this equation here. Okay? What kind of equation does this look like? Think back, math. Yeah. Slope, intercept. Y is equal to AX plus B. Okay? We actually use the same A. Or MX plus B. Okay, we'll do it that way. This is your y-intercept, or your vertical intercept. This is your slope, and this is your horizontal variable. This is your vertical variable. So guess what that would be? Velocity as a function of time. Velocity is your vertical variable. Time is your horizontal variable. V0 is your vertical intercept, and the slope here is A. So yeah, that gives you a straight line formula for velocity as a function of time. You know the initial velocity. All right. Yeah, there's a couple more ways you can play with it, but I think this is the V0 tells you how far up you go, and then the AT tells you how much increase in velocity you go from then All right. What about this one? Yes, displacement is a function of time and acceleration. Okay? V0 is just a constant there, like 1/2 the constant. Obviously, you use this when you don't know and are not asked to find final velocity, because that's nowhere in the problem. This is the original or initial velocity. The area under this graph, V versus T, for any object is equal to the displacement of the object. Okay? That's not as obvious as the rest of them. The others make pretty much sense. Let's see if they give something to help explain that last one. No, they don't. Okay. The area under the graph of V versus T that would give you just leave that alone there, I guess. Can't think of any way that makes it a lot clearer. I can think of a few things, but they almost muddy the water. Okay, how about this one? What are we missing? Velocity as a function of acceleration and displacement. What are you missing? It's one variable you're missing there. Time, exactly. Okay. When you don't know and aren't asked for time. All right, here's the problem solving. Seems like we've hit these in a couple of other places too, haven't we? I'll do one just by every chapter, I think. Read the problem. Okay? Now, I just don't read the problem when I'm reading the problem. I also start drawing pictures when I read the problem. Okay? Pictures are worth thousands of words. I also start listing. Okay? Listing what they give me in the problem. Identifying what it is, what variable it represents, that kind of stuff. Now, in drawing the diagram, choose a coordinate system. If you're horizontal motion, make it a horizontal displacement. If it's vertical, make it vertical. Okay? Choose a coordinate system. Later, we'll have two-dimensional systems. You could even have three. We're not going to do much with three this time, but you know. Label as best you can the initial and final positions or points of your situation. Indicate what direction is positive for displacements, velocities, accelerations. I shouldn't have left off displacements, since they're also vector quantities. Now, label all the quantities. I said I was listing them. List them with what they are, including units. Okay? But be sure the units are consistent. If they're not, if you notice that some of the things are given in inches or centimeters and others are given in meters, then you're going to need to convert one to another to make sure you've got. If your units aren't consistent, the numbers make no sense. Convert if you need to. If you need to get those meters to kilometers or centimeters to meters or whatever, convert whatever you need to. Choose the appropriate kinematic equation. Those are the 4 or 5 we were just looking at. Choose the one that deals with all the things you were given and the thing you're looking at. Doesn't deal with something that's not even there or has no bearing on the problem. Okay. Once now this is the book's approach, and a lot of mathematicians and physicists go by this. I say use whatever you want. It says solve for the unknown first. In other words, if you got the kinematic equation, okay, you know they gave us this piece, they gave us that piece, we're looking for that piece. Okay? You got the equation written here. They say solve for the one you're looking for. Literally, just with the letters. Don't plug in any numbers yet. I call that chug and plug. Okay? Now, once you get them solved for that, you may have to solve two equations for two unknowns if that's the case. They don't say anything about plugging in the values. So you can either solve for the unknowns before you plug in or after you plug in. It doesn't matter. And then plug in at the other time. Okay. They usually they give that a separate step. Check your results several ways. One very basic way, does this make sense? If you got a ball falling at 3,000 miles per hour, probably not, okay? Balls don't go that fast, you know. If you got protons having a mass of a kilogram or so, probably not. Protons aren't that big. So check and see if the result even makes sense, okay? Including the units. If you have something in seconds per meter squared, you don't have anything because there's nothing with that unit. Meters per second squared, that would be an acceleration. So if you're trying to get one thing and you got something with seconds per meter squared, or meters per second squared, which is acceleration, but that's not what you're looking for, you've done something wrong. Other things they say, estimate and compare. Use simple numbers that you can do easily in your head and see if they come up with about the same thing you get. Okay? I don't want to beat that one too badly. All right. There's your kinematic equations, problem-solving strategy. They have a couple of examples here. One's Daytona 500, one's a car chase. If you want to see any of these worked out, I'll be glad to. And there's another one, a runway length. Have you got enough runway to stop the plane or get it taken off before you crash? Might be an important thing to know. The accela, which I'm pretty sure comes from the word acceleration, but I'm not absolutely certain, is currently in service on the Washington, New York, Boston run, and they give some numbers for it here, some graphs, and you can play around with that. Again, if you want to see this done, we can do it. That one particularly does take a bit of estimation and guesswork. Okay. Anyone want to see any of those done? That was 4 examples. Daytona 500, car chase, runway length, and accela. They call it the Porsche of American trains. Well, if not, we're moving on to 2.4. This handsome-looking character here is Galileo Galilei, or I guess is how you pronounce that second one. Lived 1564 to 1642. And if my math is right, that's about 78 years. Pretty good for a man back in that time. Okay? He formulated some of the laws that govern the motions in free fall. Combination of him and Isaac Newton, this is sort of a bizarre thing. Now, it depends on the calendar you go by, but Galileo was the first one to really question Aristotle's rules for motion. Aristotle, way back, had been this brilliant Greek philosopher and scientist, sort of, so to speak, and he came up with a lot of observational ideas about how motion worked. Some of these didn't fit too easily together, so he had to split things into celestial sphere and terrestrial sphere. And he had different laws for different ones because he said they just obey different laws. We know today that's not true, but he thought they did. Well, Galileo was one of the first guys to come along and say, you know, is this really true? It makes sort of sense, but is it really true? That's the thing. Aristotle and all the ones way back then just observed and wrote down their best guess of what happened. Galileo started the process of observing, guessing, testing. If he made his guess, come up with a suggestion, test the suggestion, do an experiment, see if it works. If it doesn't, revise your test. See, Aristotle never did that. He said, these seem to work, let's go on to the next thing. He never tested, so to speak. Well, Galileo started that, and he formulated the laws that govern the motion of free fall. Now, he did that using inclined planes, relative motion. He came up with one of the earliest thermometers that kind of worked, pendulum, pendula. He was way ahead of the game in many areas. Now, he got the process started. Isaac Newton came in later and sort of polished it off. Okay? Now, as I was starting to say before, depending on what calendar you use, the same year that Galileo died, or the next one, Isaac Newton was born. Some books have Isaac Newton being born on Christmas Day the same year, and others have him being born early in January on the next year. Okay, but it's just literally months apart, less than a year apart from Galileo's death to Newton's birth. Of course, they never interacted, they never exchanged things, but Newton was later able to study Galileo's work, and in doing so, built on it big time. Okay, in just about every area. Okay. If you haven't noticed, this could be a good paper topic. I don't think anyone's wrote. Has anyone chosen him already? Oh, you did. That's been taken. Okay. If you want to work on some of the things he did, are you doing his life or some of his experiments? His life. Okay. So if you wanted to see, say, work at Galileo's proposal on free fall, not dealing with his life but doing that, that would be a good other topic, or thermometers, or any of this. So the book has a little blurb. It doesn't have this handsome picture of him, but it does have a little blurb in the right-hand corner of page 49. Now, why am I saying that? This cannot be used as a source. This can give you an idea to go to some source other, but you cannot have the source as your book. Now, they also mention several other things here, and they mention several other names in here. When you're dealing with, gracious, my head hurts. When you're dealing with let's see. Let me back off and start again. A few things about Galileo, and you'll probably run into this of interest to you. Okay, I got where I was going before. When you read this, you'll see other names mentioned. Okay, one of these predominantly here is Copernicus. Okay, that would be a potential paper topic as well. I don't think they mentioned the guy who first invented the telescope, but Galileo perfected the telescope, okay, or at least improved it big time. And okay, what did Copernicus do? What was he known for? Anyone know? He was actually the first to do this, but he was the first in sort of more modern times. Before Copernicus, most of the scientists, yeah, what? He put the sun in the middle? Yes, it's called the heliocentric model. He put the sun in the middle, in the center of the solar system, and then he could explain the motion of the planets around the sun, and he could do a tremendously better job than Ptolemy and some of the others did trying to put Earth in the center. Of course, all of us think we're the center of the universe, right? Unfortunately, true. But we're not. We're a little speck of dust flying around an insignificant star in a great big galaxy that's just one of billions of galaxies out there. And yet, the early thinkers thought we were the center of the universe. And it sort of made sense. If you look at the sun over the day, it seems to rise in the east, go overhead, and set in the west. It looks like it moves across the sky. It moves around the earth. It doesn't, but it looks like it does. If you go out and look at the night sky, it looks like the stars move, right? And it actually looks like they rise in the east and go overhead and set in the west, and they just keep doing that all night long. Different stars come up and move. Sun, they come, you can't see them set, but it just looks like they're moving around the earth. So it does look like we're the center of the universe, right? We're not. Unfortunately, the early philosophers who came up with this, all that philosophy got sort of tied in with our view of ourselves, this is sad, in our religions, including Christianity. Okay? And there's really, I can't find anything in the Bible that even remotely suggests we're the center of the universe, and yet many religious thinkers assumed what it was saying implied that. So when Copernicus came along and said, nope, the sun's the center of the solar system, they went up in arms. Good news for Copernicus, he lived over in Poland somewhere. The church was down here in Italy, Roman Catholic Church, So he was a long way away, and even though the church hated what he was doing, he was fairly safe from it. The bad news for Galileo is when he started reading about what Copernicus came up with, he looked into it himself. He said, this guy's right. Then he improved the telescope, and he could look at some of the planets, and he did, including Jupiter. And when he looked at Jupiter, he saw 4 large moons that went around Jupiter. He said, wait a minute. And guess what? He could see that Jupiter spun. He could see that the moons were spinning. He also, I think, was able to see the sun spinning. He said, wait a minute. If you take this spinning motion along with what Copernicus said, it makes perfect sense. If the Earth is really spinning, that makes it look like the sun and the stars are going around us, but they're fixed in space. Then the planets, which really did all sorts of weird things, you could account for their motion around the sun while we're moving around the sun at a different rate, and that's why they sort of wandered all over the sky. In fact, the word planet means wanderer, okay? Because they didn't follow nice patterns like the stars of the sun did. The moon was in a class by itself, but it followed the regular pattern. Because that's the one object that did go around us, the Earth. So, unfortunately for Galileo, when he started supporting Copernicus, guess where Galileo lived? Italy! He was not out of reach of the church. He was very much within reach of the church. And if he hadn't been such a prominent scientist, big deal person, he probably would have been executed. As it turned out, they put him under house arrest, threatening execution unless he recanted support of Copernicus' theory. So he said, all right, I don't believe it, He really did believe it, but to save his life, he claimed he didn't. He continued writing about it, but just didn't have any of his work published until after he died. And then he said, yeah, I really believe this all along, and here's more evidence to support it. So he was really a pretty interesting character. Okay, way more than we needed there. Okay. like I'm saying. There's lots of really great stories out there, things that went on in the background. When we're talking about free fall, what do we mean by that? A freely falling object is any object that's moving freely under the influence of gravity alone. Do you think anything really is in free fall? Just about always you have some other influence there. But most of that is air resistance. Now, if you're in a car driving down the road at 70 miles an hour and stick your window out of the car, you're probably almost going to dislocate your shoulder because air resistance is going to yank your arm back like crazy. So don't do it, okay? So if you're going fast enough, you notice there are other forces out there. But as long as you minimize those forces, you can treat things as if they're in free fall. In other words, just deal with velocities that are small enough. Free fall does not depend on the object's original motion. Okay? Now, do you think this would be free fall? I'm not actually, I'll use this. I'll hold this up here and drop it. Yeah. There's very little thing acting on this except gravity pulling it down. That's sort of free fall. Now, there is a little bit of air resistance. If this was coming from way outer space, falling for a long enough, acceleration for long enough, yeah, it gets fast enough, the air resistance makes a difference, it would melt because it would have so much resistance. That's what meteorites are, okay? So, as long as it's not much else. But what if I took this same object and threw it into the air? Is that free fall? Not as long as I'm throwing it. But as soon as it leaves my fingers, then free fall takes over. So it doesn't depend on the object's original motion. Yeah, as long as I'm pushing it up there, I'm exerting a force on it. But as soon as it leaves my hand, it's in free fall. Now, it's not falling, it's actually going up. But it's slowing down, and it is, in a sense, falling. Because it's slowing down to something moving. All objects falling near the Earth's surface fall with a constant acceleration. Okay? All objects falling near the Earth's surface fall with a constant acceleration. That all depends on, and I mentioned them earlier, another really good paper topic. Has anyone chosen Newton yet? Yeah, okay, you did. Okay. So Newton's out, but you can talk, are you doing his life or something else? Life, okay. If you want to do Newton's theory of gravity, he did that one. Development of calculus, he did that one. Color, he did that one. Motion, he did that. I mean, Newton did a ton of things, so you could, if she's got his life, you could write about one or the other. Well, one of the things, why did I bring him up? I can't remember. All objects falling near the Earth's surface fall with acceleration. Okay, yeah, gravity, I guess is what it was. He came up with the first description of what gravity is. It seems odd. No one had even thought about what causes gravity, okay? You just knew it was there, but they just assumed it was always there. Newton was the first one to do that. And so he came up with a formula that defined it and described it, and we still use it today. The acceleration is called the acceleration due to gravity. It's indicated by the letter G. Okay? Now, I can't remember if I mentioned this before, but you're going to run into it, so let me mention it. I probably have said it before, back in the last chapter. Okay? When we have formulas like this, okay? These are called parameters. They stand for quantities. velocity, acceleration, displacement, time. Okay? Now, displacement, X. What would be some units we could use to measure displacement? What's the SI unit for displacement? Meter. And that's given the symbol M. Okay? Why is this stopping? Okay? Okay. We're not there yet, so okay. I'll just go back and say it. So if you see a number in front of the letter M, usually that means so many meters, right? In a short time, like a chapter or two, we're going to run into a formula F equal MA. What is that M? It's not the unit meter, that's the quantity mass, okay? The reason I brought that up, what do we measure mass in? SI unit. Talked about this last chapter. SI unit for mass? Kilogram. Kilogram. The smaller unit from that is gram. So if there's a number in front of a G, that means so many grams. However, if G is used in a formula, that's the acceleration due to gravity. And that's what I'm getting at, is that we use the same letters for different purposes. If there's a number in front, that's a unit. Don't confuse that with the letter that stands by itself and is a parameter in an equation. G is a parameter in an equation standing for the acceleration due to gravity. G after a number is the symbol G for gram. So that's why I wanted to say that here while it was on my mind. M stands for meter if there's a number in front of it. M stands for mass if it's in an equation. We haven't hit any of those equations yet, but we will. I promise. Yes? It's what? I was just thinking of that. If we can finish, yeah, we're awfully close to having a lab. The trouble is we may not have time to finish it today, or we might. I think we do. It's a fairly short lab. So what I think I'll do is sort of quickly go through this, and technically the lab, to give you a 2-hour lab, I should have stopped at 3:30, right? It's already past 3:30, but class is supposed to go till 3:50. I think I can finish this by 3:50. That'll only give us an hour and a half for lab. If we need an extra 30 minutes, we'll take it next time, but I don't think we will because it's a pretty short lab. So I'll zip it and start moving on with this a little bit faster. Okay. Acceleration due to gravity is symbolized by the letter G, and then the SI unit is 9.80 meters per second squared. SI unit is 9.80 meters per second squared. Now, most of the time, you'll see it 9.8. I don't know why this book, I think I do know why it put the 0 there. So if you add 3 significant digits, you can keep them. But a lot of times, we'll just use 9.8. Now, when you're estimating to see if you're in the right ballpark, you can use 10 and you're going to be awfully, awfully close. Okay? So that's only an estimate. If you want more precise, use 9.8 or 9.80. Now, acceleration is what kind of quantity? Scalar or vector? It has a direction, always. So it's a vector quantity. Okay? G, being acceleration due to gravity, guess what direction it's pointing? Toward the center of the Earth. No matter where you are, What's your surface you're on? Gravity points toward the center of the earth. Always straight down toward the center of the earth. Now, free fall that we were talking about before ignores air resistance. There's always a little bit of air resistance. The greater velocity you have, the greater the air resistance. So once you get past a certain speed, you can't ignore it anymore. But for most of the speeds we're going to deal with, we can ignore it. Okay? So ignoring air resistance and assuming that G does not vary with altitude. Okay? Now, if you remember backward, just a slide or two, near the Earth's surface, that is a constant acceleration, G. If you get way up there, it's not a constant anymore. It actually falls off, okay, because you're too far from the Earth. There's a 1 over r squared dependence, and the r starts at the center of the Earth, so you have the whole radius of the Earth. Anything you drop up here on the surface is negligible compared to the radius. Once you get way out into space, it's not negligible anymore. So that's why, as long as you're fairly close, short vertical distance above the surface of the Earth, yeah, you count it as you count the acceleration as a constant, and that that doesn't vary with altitude, and you ignore air resistance. If you do that, free fall is constantly accelerated motion. Constant acceleration is also called uniform acceleration. Very good. Okay. So here's your object. This time, I'm going to drop it. Now, if I drop that, I'm really not going to drop it. I don't want it to break. This is my valuable pencil sharpener. Okay. So, if I were to drop it, what can you tell me about its initial velocity? I just release it. Now, I don't throw it. I drop it. What's its initial velocity? 0. If I throw it either up or throw it down, I've given it an initial velocity, non-zero. But if I drop it or release from rest, when you see those terms, that means initial velocity is 0. Now, even though everything moves that way, if you let up be positive, which is where it is most of the time, that's your convention, then G is always a negative number. And what number would it be in the SI units? Negative 9.80 meters per second squared. Remember, it has units too. Okay. Now, once you have that, use your kinematic equations. Generally, we use y for vertical motion rather than x for horizontal. So they'll look a little different, but they're right there. Acceleration in the vertical direction, as long as you're ignoring air resistance and you're not firing a rocket or something like that, your acceleration is always negative 9.8 meters per second squared, meaning down, going toward the center of the Earth. It has a sign, it has a value, and it has units. Okay? So your acceleration in the kinematic equations, you can change to be G for free fall, and G is always negative 9.8 meters per second squared. If you release from rest, initial velocity, an object thrown downward, I'm sorry, I didn't read the title. Your acceleration is still that. It doesn't change. Once it leaves your hand, now yeah, as it's in your hand, you're accelerating it. But the second you leave your hand, even if you're throwing it, now the only acceleration is free fall. The acceleration due to gravity. But if you throw it, then your initial velocity is not 0. If you throw it downward, then your initial velocity is negative. If you throw it upward, then the initial velocity is positive. Okay? So it just depends on what direction you throw it. Now remember, we're doing one dimension only, so we're not doing it at an angle. That's next chapter. We're only throwing up or down. Don't throw up. No, I'm just kidding. Okay. So, if you throw upward, okay, then the initial velocity is positive. But what's your acceleration? your hand, the only thing acting on it is gravity. So initial velocity is upward, so it's positive. The instantaneous velocity at the maximum height is 0. Okay, let's get that. You throw the ball or the object up, straight up, absolutely straight up. Okay? Now, as soon as it leaves your hand, you gave it an initial velocity. Give me a velocity. Make up one. Make up a velocity. Second. What? 6? 6.2. How about 60?
Okay.
Let's do 60. The reason I want to do 60 is this. Let's say I'm throwing it up with a velocity, initial velocity of 60 meters per second. I'm not saying I can do that. Let's just imagine I did. As soon as it leaves my hand, what's the initial velocity is positive 60 meters per second. But what's its acceleration? Downward. Now let's round that to 10, just for my illustration purposes. Negative 10. So that means in the first second, what's its velocity? 50 meters per second, because in every second, it loses 10 meters per second every second. That's what the acceleration means. So after 1 second, it would only be going 50 meters per second upward. How about after 2 seconds? Losing speed at 10 meters per second every second. That's what this says. Minus 10, we go around that to 10 meters per second. So now it's 40. After 3 seconds, 30 after 4 seconds, 20 after 5 seconds, 10 after 6 seconds, 0, which means all that time it was going up. Initially pretty fast, but then all the way along slowing down. Now it's slowing down constantly. It's not doing like that. It's slowing down constantly as it goes up until that 6th second it's lost all its speed whatsoever. So the instantaneous velocity at the maximum height is 0. Because as long as it's got any velocity upward, it's still going to be going upward. But when it goes to 0, it stops just instantaneously and starts falling back down at guess what rate? 10 meters per second, okay, using this, downward. So after 7 seconds, guess what? 10 meters per second downward. After 8 seconds, 20 meters per second downward. After 9 seconds, it keeps going up. And after on the 12th second, guess where it is? Right back where it started, because for everything it went up, it came down just symmetrically. Okay? And therefore, at 12 seconds, it would hit me on the head. Okay? Now, shouldn't be taking the time to do this, but hopefully you've not been around anyone like this. Hopefully it's always somewhere else. But unfortunately, I think it does happen in the U.S. a little bit. But in some parts of the world, when people go out to celebrate, especially warriors type thing, they fire the weapon into the air. Not a very good move. Because if that person fired it exactly, perfectly straight upward, and let's say that bullet, make up a bullet velocity. On the ballpark figure. Second. 70 what? Okay, they are much faster than that. Let's say 600 meters per second. Okay? I don't know if that's reasonable, let's say. That means you fire it 600 meters per second up, straight up. In 1 second, it's going 590. Then another second, 580, 560. Going on ways. It's going really fast. It's taking a long time, but at some point it's going to stop and then start coming down. And every second on the way down, it's going to pick up speed and pick up speed. And guess what? It's going to be right at the time it gets here. let's say 600 meters per second. So if you fired it straight up and you stood right there, just like shooting yourself. Now, the odds are you're not going to fire it straight up. You're going to fire it at a little bit of an angle, right? I mean, somebody standing over there could get shot in the head, or in the body somewhere. Because every bullet that goes up at a certain speed generally comes down at the same speed. Even though somewhere up there actually physically came close to stopping. But then by the time it came back down, it was going at almost the initial muzzle velocity. Now, not quite, because you got air resistance, but it's still close enough. And I remember when my wife and I moved here to Birmingham, I think it was in the first year, I think it was that first summer we were here, we heard on the news this couple was in a pickup truck with a club cab, and they had a kid in the back, car seat thing, and they were going down the interstate. It was fine, and there was some noise, not super loud, but some noise they heard. They looked around, they thought some car had backfired, got their car rolling into place, so they kept on going. Some point probably glanced back and said he'd be sleeping. It wasn't sleeping. Someone had been hunting or doing target practice or something in the field far, far away. No one knew where. And the bullet went up, and it come down, right to the back of the window. Nobody's fault, just a weird. Truck was just at the wrong place at just the wrong time, but it was tragic. Okay, so the instantaneous velocity does reach a zero at the maximum height, but then on the way down picks up every bit of velocity that it lost on the way up, coming back down. Now, this shows a little bit of a displacement, because we didn't want to go the same line. You throw it up, but at some maximum height, velocity zero, then it starts coming back down. And if it got to the same place it started, if it's only doing free fall under the influence of gravity alone, no air resistance, the same speed coming down, just in the opposite direction as it was going up. All right. The motion may be symmetrical. Okay, that's what I was just saying. The time up is the time down. Velocity up is opposite the velocity down. Okay, it's always opposite direction there, but the magnitude is the same. The motion may not be symmetrical. This is a pretty lousy bullet here because it's not real clear what it's talking about, right? Oh, okay. If you have motion, let's see if they have an example of this. I was going to do we're almost at the end. Let's do the quick quizzes real quickly. Quick quizzes, okay? A tennis player on a serve tosses the ball straight up. While the ball is in free fall, does the acceleration increase, decrease, increase then decrease, decrease then increase, remain constant? Do I need to say it again? A tennis player on serve tosses the ball straight up in the air. While the ball is in free fall, does its acceleration increase, decrease, increase then decrease, decrease then increase, or remain constant? Say again? Okay. You're thinking speed. Okay? When you throw the ball up, the speed decreases, then increases, then increases. The acceleration, though, under the influence of free fall alone, the only acceleration on the ball is A is equal to G is equal to that everywhere in the motion. It's constant. Constant. Okay? This is 2.6 E. Absolutely correct. Okay. As the tennis ball in that question travels through the air, Does its speed, increase, decrease, decrease then increase, increase then decrease, remain the same? Second? Decrease then increase. I gave it away. Sorry, I didn't know that was the next question. So that indeed is C. Decrease and increase, yeah. Okay. 2.8. A skydiver jumps from a hovering helicopter. Helicopter is not moving, it's just hovering. The skydiver jumps out of the hovering helicopter. A few seconds later, another skydiver jumps out. So they're both falling in the same vertical line relative to the helicopter. Assume both skydivers fall with the same acceleration. Let's assume maybe it's gravity, okay? Does the vertical distance between them increase, decrease, remain, or stay the same? What you think? Relative distance between them. Okay. All right. That is, yeah, there's two answers here. Okay. I think it actually increases. Let's see which it is in the back. No, it says the... Now, yeah, it does increase, and here's why. The first diver jumps out, okay? Now let's say it jumps horizontally, so there's no initial velocity. Initial velocity is 0. So gravity starts pulling him down. So at 1 second later, he's going about 10 meters per second. Initially 0, then 10 meters per second. Now how many seconds later before the second diver? You tell me. 4 seconds. So, first diver jumps out. The first second, 10 meters per second is his velocity. Second, 20. Third second, 40, 30. The next one, 40. If he hasn't splashed down yet, this one goes, he starts at 0. So this one's going 40 meters per second. This one's starting at 0. The distance actually increases. Okay? Now, the second part of this question says, does the difference in their velocities increase, decrease, or stay the same? Okay? The difference in the velocities was 4 seconds later. This is 40 meters per second. This is 0. The next second, this is 10. That's 50. The difference is still 40. So that stays the same. It's the difference in their velocities stay the same, but the velocities is always increasing. So that indeed is A for the first part, F for the second part. All right. Now this is one of the examples in the book, so let's do this one. It should go pretty quickly. Okay, and this is one that we're dividing the motion into segments, though it's not absolutely necessary. The symmetry portion, okay, yeah. This is not, okay. Remember when I said this is a pretty lousy slide? It said, motion may not be symmetrical, break the motion into the various parts. This one is not symmetric. It's symmetric from here to there, but since he started on top of the building, and the ball goes to the bottom, that's where you lose your symmetry. So this one will break into parts, okay? Let's read the problem. A ball is thrown from the top of a building within it, doesn't say where, but it's thrown straight up, according to the picture. From the top of the building with initial velocity, oh yeah, there it says it, 20 meters per second straight upward, okay? At an initial height of 50 meters above the ground. So the building is 50 meters tall, or at least the building and wherever his hand is when he releases the ball. So he's throwing up with 20 meters per second, straight upward, initial height 50 meters from above the ground. The ball just misses the edge of the roof on the way down, okay? shown in the figure, determine A, the time needed for the ball to reach the maximum height. So there we need time. Okay? So what kinematic equation? We've got, let's see what they tell us. VI, or VO I think they use here. VO is 20 meters per second, and this is upward, so that's a plus. What else do they tell us? Initial height, so this is our Y naught, is equal to 50 meters, 50.0 meters. Okay? They've already drawn the picture. I'm not going to draw the picture, so let's use the picture. Okay. Determine the time needed for the ball to reach the maximum height. Now, there's something else that we know here, but they didn't say it. What do we know with every free fall problem? G. And what is G? Gee whiz. What is G? That is also our acceleration. And what is it? Its value? Negative 9.80 meters per second squared. Okay? And guess what we're looking for? T. This is the unknown. So we want a kinematic equation that has time, acceleration, and we can't have initial velocity. Let's see, what is the other thing we got? I guess the Y. You know, we know what the Y is, and it's going on up there. Okay. So what kinematic equation do you think we'll use? And by the way, if you flip you have to go back to page page 44, table 2.4. That gives your kinematic equations in terms of x. Okay. Oh, here they go. No, I thought there was a place that gave them in terms of y. You have to turn a few pages over. Well, they don't ever list them for y. So we'll just have to change y to x. Okay? But if you look at the top of page 40, there they list most of them. Okay? Now, you're not asked about its velocity, so I wouldn't use the first one. There's no delta y there, so I wouldn't use the second one. It looks like to me, and we need time in it, so it looks like probably we will use the oh, yeah. There's something else. Well, no. Yeah. We know V final, don't we? I forgot that. To reach its maximum height, guess what the V is? V final is maximum height the instantaneous velocity at the maximum height is 0. Whoops, hit the wrong button. So V, I'm not going to say V final, V is equal to 0. So we do know V, okay? So that looks like, and we're looking for time, that first equation. I'm going to rewrite it in terms of this. V is equal to V0 plus AT. We're looking for time. We know A right here. We know V0 right there. And we know V, the final velocity, is 0. So, do you like to plug and chug or chug and plug? We're looking for this one. You want to solve first for that, or you want to plug in the numbers and then solve for that? I don't care. Your choice. Two choices, either one of them is fine. Which way you want to do? Plug and chug or chug and plug? Second? Plug and chug. So let's plug in the numbers first. 0, final velocity, is equal to 20.0 meters per second minus 9.80 meters per second squared times t. T is what we're looking for, so that's the variable there. So how would you solve that for t? Trying to find the t. Earth to class, come in please. Say again? I wouldn't. If t was to a second power, yeah, factoring would be a good idea. T's to the first power, let's just solve for t. So let's get t on one side and things without t on the other side. So let's add 9.80. I'm going to leave off the units for now, t to both sides. I really want to leave off the 0 too. That's equal to 20. I want to leave off that 0 too because they're not really helping me. And then we divide by 9.80. And what does that give you as t to be? Anyone got a calculator? Second? 2.04 seconds. Where is it? Right here. 2.04 seconds. Now let's see if our units are right. I left off the units. This was in meters per second. This is in meters per second squared. The meters go out, and 1 of the seconds go out. And what we're left with is a 1 over 1 over second. Flip that over, and that gives you seconds. So you're certainly correct. 2.04 seconds. And that's what they got up here. Okay, so that was the first one. Okay? Oops. Okay. The B question. What is the maximum height? So this time we're looking for y. We know one more piece of information. T is equal to 2.04 seconds. So now it's asking for y. What is the maximum height? What formula do you think we would use then? Well, I hate to keep turning you back to the back, so backwards. Let's go forward just a couple pages, and it's one-dimensional motion with constant acceleration. There's a 2.6, 2.9, and 2.10. We left off 2.87 and 2.8, but we can live with those. We're looking for y. The first one we had no x's or y's in them. The second one, though, does. And we know everything that's given there except for the delta x, or delta y in this case. So let's first do delta y is equal to v naught t plus 1/2 at squared. You see that formula? Okay. Now we know everything we need now. That delta y is v naught was, okay, you want to, it's already in the form you want it, so let's just plug in. 20.0 meters per second times your, we just calculated 2.04 seconds. It's going to be a minus 1/2 because your A is G, which is 9.80 meters per second squared, times 2.04 seconds squared. Okay? Now, the seconds cancel out here. Second squares cancel out there because you square the units as well as the number. So let's just do our multiplication. 20 times 2.04 would be 40.8, I think, isn't it? You got a calculator to do it. And that would be meters minus 1/2 of 9.8 would be 4.90. But we got to square 2.04. So someone with a calculator do that for me quickly. 2.04 squared. 4.16. Is that right? And that would be, okay. Now, with your calculator, do all that at once. 40.8 minus 4.9 times 4.16. 16 from, make it 20 from 40. So around something less than 20. Have you got a number? Anyone? 40.8 minus 4.9 times 4.16. $20.1, 20.4, and that would be meters. Now that's delta Y. What does delta stand for? Y final minus Y initial, right, is equal to 20.4 meters. But our Y initial was 50 meters, right? So we take that 50 and add it to both sides. So we've got the final position is 70.4. I'm running out of room, so that's why. 70.4 meters. Let's see what they got. Okay. They said Y max was 20.4, but they didn't add the 50 to it. I don't know why. Seems like it should have been added. But we can live with that. Okay. What do they show down here? They say 20.4. That's actually a delta Y. That's not really Y max, but I don't know. From the top of the building, that's your Y max. And, oh yeah, that's where they have it up here, 20.4. Okay, I didn't see it. There it was. So that gives you that one. They'd use this number rather than really adding from the ground level. Okay, what's the next question? The time needed for the ball to return to the height from which it was thrown. Any ideas on that? Oh, by the way, I did see some people come in. That was Raven, is that right? Yeah, okay. And Bria, right? Yeah. All right, good deal. And y'all, oops, y'all made it in for the loud part, not the, I don't know if we're going, I was going to do this fast and I really didn't. Okay. need the call roll again. Okay. Now, next thing. The time needed for the ball to return to the height from which it was thrown. Any ideas on that? Remember symmetry? If it took 2.04 seconds for it to go up to the top, it takes another 2.04 seconds for it to get back. That adds to the 4.08. That's just symmetry. You don't need to use a formula for that. At the same time it took it to slow down and go up, speeding up and coming down at the same time. So add to just double that time to 4.08. Okay, so I'm just going to check that off. Okay, right there. Now there was another part to that C, and the velocity of the ball at that instant. Okay, at the instant when it was back at the same level. Any ideas on that? Okay, let's go back to this. The motion may be symmetrical. T up is equal to T down. So it was 2.04 up, 2.04 down. That gave you 4.08. But look what else. Then V is minus V naught. What was your V naught? 20. So your V now is going to be minus 20. So that's where they get this one. So that, the C part, took basically no new calculations, just using symmetry. Does that make sense? Now let's look at the D part. The time needed for the ball to reach the ground. Okay? Now, if we're using everything that we used before, then the ball falling from here with this initial velocity, now you change the initial velocity, still acting under the influence of gravity, the time that it takes to reach the ground, go back to this formula. Okay? Nope, not that one. Because you don't know the V at the bottom. So that won't work there. I believe it's this formula. Okay? Because you're looking for T, you know A, you know V0, it's going to be that new V0. And you know the delta Y, that's going to be 50 meters. Yeah, this is exactly what we need. Okay? Now, I'm going to write it out for you, but not solve it, because you really need to solve this yourself. Okay? So here's what we're going to write. We're going to use this formula, but with these new values in it. The delta Y is 50. You're going from here to the ground, that's 50 meters. And actually that's going to be minus 50 meters because it's downward. So minus 50, I'm going to leave off the units for now just because they cloud up the problem so badly I don't have room, is equal to, your V naught is now this one, minus 20, I'll leave off the point zeros too, times T, and that's what we're looking for, the time. And then we have minus 1/2, 9.8, I'm going to leave off that 0 too, times T squared. Okay? Now notice everything has a minus in it, right? So you can multiply both sides of the equation by minus to leave plus. And I'm going to rearrange it too. Half of 9.8 is 4.9 T squared plus 20T. And then I'm going to move this to the other side, minus 50 is equal to 0. Any idea why I did that? I want to get everything on the same side. Now, Ryan likes to try to factor. Do you think you can factor that one? If so, you win a prize. I don't know what the prize is, but if you can factor that, yeah, you win big time. When you can't factor, how do you solve a problem like this? Help me somebody. What kind of equation is this? Maximum exponent of 2. We have a name for that kind of equation. linear, this would be a linear equation. If the maximum exponent is 2, it's called a, sounds like 4, but it's not, quadratic equation. And if you can't factor a quadratic equation, what would you use? Why did I try to get you to say the word quadratic? Use the quadratic formula, of course. Someone remind me how that goes. Here your variable is t. T is equal to quadratic formula. Somebody. Minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. You got it. What in the world is that, a, b, and c? Those are your coefficients of your standard form. Here's the a, there's the b, there's the c. So that will be, I just don't have enough room. Can I erase some at the beginning? I think I'll do that. I wasn't going to do this, but it seems like I'm having to pull too many eye teeth to get you to do this. So let's go over this. We already got that answer, so we'll leave the answer. Okay. So the b here, so here we have t is equal to, b is minus 20 plus or minus the square root of b squared, which is 400. 20 times 20 is 400. Minus 4 times a was 4.9, times c, which was negative 50. Whoops, 50. All divided by 2 times a, which is 9.8. Okay? That's going to be the time as soon as we get it done. Now, before we go too much further, a couple of things to note. Before I get in here, I'll look at this and count my minus signs. The minus 4 is always a minus. That's a plus, that's a minus. If you have 2 minuses, that becomes a plus. Right? So I can do this. Okay. Now, if you did the minus and minus here, the numerator is going to be minus, the denominator plus, that's going to give you a negative t. Guess what? You don't have any negative t's. You only have positive t's. T that it's going to take to hit the ground, you're going to. So we're going to forget about the minus here. So if you got a calculator, you can do it in 2 parts or you can do it in 1. I don't know. Might be easier to do it in 2. Let's first do this thing in here. Well, depends on what kind of calculator you got. Okay? If you got a nice fancy calculator, you can do this just right. Try it. Negative 20. Now, most of the time, you're going to hit the minus in parentheses key. What kind of calculator you got? Is it just plain old scientific? Well, it's a display type. Okay? On your display type calculators, this minus sign is your subtraction key. The minus in parentheses is your negation key. You hit that first. Now, if you have an old scientific, you have to put the number first and then hit the plus minus key. You have a fancier one than I do. So you hit that key first. So it's negative 20. That minus key at the bottom, 20, not the one at the subtraction key. Negative 20. We're only going to do the plus. Then do your square root symbol. And it opens a parentheses for you, doesn't it? Okay? So in that parenthesis, you do 400 minus 4 times 4.9 minus 50. You multiply all those things together, not subtracting. So let me say that again. In the square root, you open parentheses, 400 minus 4 times 4.9 times negative 50. Again, use that little subtraction, the little minus of parentheses key, 50. Then close the parentheses for your square root, and then do divide. Then do equal, and then divide by 9.8. Okay. Actually, it's a lot easier if you do it this way. Minus 4 times minus 50 is positive 200 times 4.9 would be 980. So 400 plus 980 would be 1380. So minus 20 plus square root of 1380 equal, and then divide by 9.8. What do you get? Anyone do that? Come on, get to know your calculators. Otherwise, doing your test, you're going to be learning your calculators and doing it from scratch. It's going to be miserable. Say that one more time. 11.74? I can't hear you. What? 4.74? 1.74. Okay, I found something a little bizarre with that. Let me think. Just look at this. Oh, I see. Wait, I messed up here. Let me see. For some, okay. Sorry. I did just from this point. The book did it from the beginning. You could do it either way. So you came out with what, 1.74? Is that what you said? So 1.745, something like that, right? Add that to your 4.08. You get something close to 1.83. That's what it is. Okay. They took it from here and did it. I just started from here and did there. That's 1.741, whatever it is, and then or 75, and then add it to that. You got it. Okay. So yeah, we got the same answer. You just went about it a different way. Number E. The velocity and position of the ball at t is equal to 5 seconds. Velocity and position of the ball at t is equal to 5 seconds. Okay? Now, in this case, you're starting that 5 seconds from the time he threw. So, the first thing it's asking for is velocity. Okay? And I've already erased it. Sorry about that. That first formula we had was V is equal to V0 plus 1/2, plus AT, right? Go back to your kinematic equation, that's it. Okay? Now, this is what you're looking for. So V is equal to 20 plus or minus 9.80. You could put the zeros in there. I'm going to leave them off. And then T. Okay. Sorry. Wrong formula. We don't have time in this one. Okay. What we're doing is velocity and position. Okay, let's do velocity first. Let's look at our kinematic equations. I always ought to have you go back and do that every time. Top of page 44. Okay, you're looking for V. Oh yeah, you do know T. T is 5 seconds. Sorry about that. Yeah, you got everything you need. Velocity is plug in 5 seconds. Okay, that gives it to you. 20 plus 9.8 times 5. 9.8 times 5 is 49, plus 20 is, that's a minus. That would be minus 29 meters per second. Okay? And put your 0 in there. Minus 29 point, okay. Let me erase some of this that's in the way here so you can see. There's your answer right there. It said velocity of the ball. Oops, wrong one, sorry. Okay, velocity of the ball, minus 29 meters per second. Just plug it in this thing. You know V0, that's what you started with. A, that's what you had all through the problem. T was 5 seconds. They told you the T. Okay? Now it says position of the ball at T is equal to 5 seconds. Well, that's your delta Y from this one. So it's delta Y is equal to 20 times 5 minus 4.9 times 25. That's 5 squared, right? Plug that into your thing. This is 100 minus 4.9 times 25. It's going to be something short of probably a little over 120. Someone do it on the calculator? 100 minus 4.9 times 25. Negative, there it is, negative 22.5. Exactly. That's at 5 seconds. Now, that took a lot longer than I intended, but it seemed like no one was seeing what to do. So, yeah, here's another one. This is example 2.10. We may not have time for it. Well, we might. I don't know. 2.10. Let me stop right now. Does anyone need a little break before we start this one? You do? Okay. Let me call roll, and then we'll take a little break and then come back. Okay, FA is still here. Nick hasn't made it in today. Tiara's still here, right? Yeah, there you are. Okay, looking in the wrong direction. Courtney with a C is still here. I've already marked. Okay. Simone Cannon, we haven't gotten yet. James Graves, we haven't gotten yet. Raven is still here. I've got her. Shakina is still here. Charity called me and said she wasn't going to make it today, but she will try to be here Monday. Courtney is still here, and she's on the way out. Okay. Ambry is still here. Where's Ambry? There you are. Okay. You're behind. Okay. Still here. Essence is still here. Ryan is still here mostly. Okay. Larius came in. So he's still here. Monique is still here. Yeah, okay. Here you were hiding too. Okay. Allison is still here, or did she just leave? Yeah, I see you. Okay. I can't see from this position. Whoa. I would skip Sasha, but you're still here too. Allison. Darius didn't make it in yet today. Okay. Scarlett's still here. Will's still here. Brianna is still here, right? Yeah, well, she was. Is she gone? Brianna was sitting up there, wasn't she? Gone for good, as far as we know, or did she just... She didn't leave any books, so I'm going to leave that blank. Naya is... Yeah, still here. And I already got Bria and Dakota still here. Okay, let's try to keep it 5 to 10 minutes or less. As soon as most people are back, we'll try to finish this last example, and then we'll talk about it. Yep. So let me pause this. I like to do the example. Okay. Explaining what happened. I went down to check to see if the lab was available that we could use, and I saw another. Oh, by the way, and then all the by the ways happened. We have a NASA grant, and the guy who we have it with likes to do guest lectures in physics. So he was asking when he can do the vibration and wave, which is our last chapter. But whenever he wants to, we can do those first if he does this one. He may choose just to do Physics 202 and 214 and do the optics of those. So that's what tied me up. I said, well, we really don't have a lot of time, and stuff. So anyway, I did that. And then when that started, I said, by the way, did you get Dr. Bryant's contract done? Because I can only do math. She does natural science. She said, oh, I thought you were going to do that. I said, well, no. So anyway, went through that and then found out I'm not getting an overload yet. Maybe I will. It's just all screwed up. But hopefully that's why it took me a while to get back, because it wasn't in the right shape. So what we're going to do is go on and finish this one example. This is it for chapter our topic 2. We don't have chapters anymore. We have topics. That was the reason you had to buy new books, so they could call them topics rather than chapters. And then we'll go on talk about what to study for the test. I can go and run off the test if we've got time. I thought we'd do the lab, and while y'all were doing the lab, I'd run off the test, but that changed now. And then, since we won't have time to do lab, we'll go on and get started in topic 3, motion in 2 dimensions, which follows real well with what we're doing here. All right, here's example 210 in your text, and here's the picture on the board here. The problem: a rocket moves straight upward. Okay, here's a rocket moving straight upward from rest. What does it mean from rest? When it says from rest, what does that mean? A lot like dropping. What's 0? Initial velocity is 0. So when you read from rest, put V0 is equal to 0. That's there, right there. Okay? So that's why I say when I'm reading the problem, I'm also drawing a picture if necessary. They've already drawn it for me, but writing down as I hit it. A rocket moves straight upward, starting from rest, initial velocity is 0, with an acceleration of 29.4 meters per second squared. Well, there's the phase 1, the acceleration, 29.4 meters per second squared. Okay? It runs out of fuel at the end of 4 seconds. So this interval here covers t equal 4 seconds. Now, the book is putting lots of extra digits there, 4.00 seconds. I probably should be, but just understand that 3 significant digits. And continues to coast upward, reaching a maximum height before falling back to Earth. Now, the maximum height, we know something else. What is that? They've said it for us here. At maximum height, we got this on several slides ago. The instantaneous velocity at the maximum height is 0. Okay? So on this one, v is equal to 0 at maximum height. Okay? Now, by the way, let's back up a moment here, and continues to coast upward. Once the fuel runs out, now there's no more acceleration upward. Your only acceleration is downward, and that's at minus 9.8. So that's for this portion. From this point on, we use this. From this point, we use, for this period here, we use that. Okay? That's why they put the bracket there. But this isn't quite true. It's this and all of this. This is also negative 9.8. Okay? So both of those are negative 9.8. Okay? Number A, or part A. Find the rocket's velocity and position at the end of 4 seconds. So let's first deal with velocity. And since we're so close to the kinematic equations here, flip over one page, and that first kinematic equation will give you the velocity because you know the initial velocity, you know the acceleration, and you know the time. Okay? So the first one says find the rocket's velocity. So V is equal to kinematic equation on flip over one page 54, equation 2.6 there. V is equal to V0 plus AT. See it? And for that first 4 seconds, this was 0 plus this acceleration, that's positive, upward, 29.4 meters per second times your t was 4.00 seconds. Here the seconds cancel out, and that's going to give you meters. So someone with a, I think I can do this one in my head. That would be 16, carry a 1, 36, 37, carry a 3, 117.6 meters. No, meters per second. Sorry about that. Oh, this is meters per second squared. Is that. So one of those cancels out, and that leaves you meters per second. Now, if I know them, they're going to list that as 118 because we're carrying only 3 significant digits. Okay? So on their answer here, they have 118 meters per second. I'm going to, if I were writing this as the answer, I'd put 118. I'm going to leave that because I'm going to use that number for later things we do to give me better precision. Okay? But yeah, I would have put the answer as 118 for 3 significant digits. The second part there said, find the rocket's position at the end of 4 seconds. Well, the position kinematic equation, again, if you turn over, that's the 2.9 on that same page 54. Okay? This will be delta x, and delta y, because this is vertical, is equal to V0t plus 1/2 AT squared, right? You're starting from 0, so the delta y is going to be your y. This will be that, so that y is going to be 0, because V0 is 0, 1/2 29.4 times 16.0 seconds squared. I went on and squared the 4 seconds. Okay? Well, I'll do half of 16 and make it 8. 8 times 29.4 would be 32, carry a 3, 72, 75, carry a 7, 1623. So it looks like about 235, and that would be this, I forgot to put my units in, meters per second squared. Now we multiply by second squared, and that gives us meters. Okay? And they got 235 meters. Now, for my purposes, for later, I'm going to hang on to the 0.2, but normally you just put 235. Everybody see that? Okay. That's the A part. Let's look at the B part. Find the maximum height the rocket reaches. Okay? Now, this is another example of this non-symmetric motion. You have powered acceleration upward here, and from there on you have free fall acceleration downward. So we're going to stop right here, or start right here, and do the rest of the problem from here. And what was the question? The B part said find the maximum height the rocket reaches. Okay? Maximum height is going to be that y again. Okay? But I'm going to do this one as a delta y, like the formula said. Now, we have an initial velocity now. Well, I'll write it down again. V0t plus 1/2 AT squared. Okay? So this is going to be a delta y. where it moves from here to the maximum height, we'll get there, so we'll just leave that as delta y, is equal to, now the initial velocity at this point is going to be this velocity right here, 117.6. Now I'm going to use the 0.6, and that's meters per second. Oh wait, sorry, wrong formula, we don't have the time. Scratch that. Okay. We're going to have to use a formula without time. Looking at your kinematic equations there, you notice that last one is the one without time. Okay? And it does have a delta y in it. And that one reads like this. If I can get my pen to come back. V squared, that's your final velocity squared, is equal to initial velocity squared plus 2a delta y. Now I'm going to use delta y rather than delta x. There's the formula we use. You see, we're looking, well, we know this. This is our 0 there. We know this. That was this value. We know a, that's this value. We're looking for the delta y. Now again, I'll ask you, do you like to solve for delta y first and then plug in the numbers? Or would you rather plug in the numbers first and then solve for delta y? I don't care. You tell me. Plug and chug or chug and plug? I really don't care. Second? Plug and chug. Okay, we'll plug in the numbers first. I've already said this one's 0 is equal to, this is 117.6. I'm going to carry my digits. Later I'll round. Meters per second, but I'm going to square it. Now it's going to be a minus 2 times, because it's a plus 2 times a minus 9.8, so I put the minus out there. 9.8, now I'm just going to leave off that for now, meters per second squared. There's a decimal in there though. You can't read my writing. Times the delta y. That's what we're looking for, the delta y. So what we'll do is change side, move the minus over there, and 2 times 9.8 is 19.6 times delta y is equal to 117.6 squared. Now I'll come back and put the units in a minute. Okay? If someone will do that on the calculator, then you'll divide by 19.6. You see? So 17.6 squared divided by 19.6. These are going to disappear here. And while you're doing that, I'm going to go on and plug the units in. 17.6, and you're squaring it, so that would be meters squared per second squared. And the 19.6 was meters per second squared. And notice the per second squareds go out, and one of the meters go out. Sure enough, that leaves you a delta y in meters, which is exactly what we want. What did you find that to be? 705.6. A little under? 705.6. 0.6? 0.6. So let's call that delta y 705. You said 0.2 or 706 then. 706 meters. So it goes an additional 706 meters up from this point. But it was at 235. Add that to 706. That gives me 941, right? So the final height is going to be 941 meters. Let's see what they got. They got 945. How did they get that? Okay. Well, they must have rounded differently or something. Okay. Yeah, and you see, here's why. Here's why. They rounded this to 1/18. Okay? And that was good for an answer here, but really what you should do is keep as much as you can, all the precision you can going forward. That's why I wanted to keep it, and that made up for the 4 meter difference. But you know, 4 meters out of 941 is not very much, so not going to introduce a lot of error there. Okay? So there is your, that was your B, maximum height the rocket reaches. Number C, find the velocity the instant before the rocket crashes on the ground. Okay, so we want V crash, okay, the velocity right before crash. Okay, now we're looking basically for a final velocity then. So we've got to use one of your kinematic equations that has velocities in it. Obviously, 2.9 would not work. It doesn't have velocity in it. So which one of these will work best? I would say 2.6. Because, no, not 2.6, because we don't know the time. So it looks like we're going to have to do 2.10 again. Yep. Looks like we've got to use 2.10. And 2.10, this is the C part. 2.10 says V squared is equal to V naught squared plus 2A delta Y. Okay. Now, we're looking for the velocity right before it crashes. So that's what we're looking for. We know the velocity. Now we're taking that as our velocity at the top. That's at 0, right? So that's real good. I can do that really easily. Here we got 2 times A. A for the trip down is that, I wrote it in here, minus 9.8. You're just under free fall there. And then the delta Y, that's the maximum height, which we just calculated. And we said 941, they said 945. We'll use their 945 so we can get the same answer they do. So basically, it's just that right there. So that will be minus 2 times 9.8 times, what do we call it, 945? Okay, 9.8 is meters per second squared. This is meters. Okay? And by the way, the velocity on the way down is negative because it's going downward. So that makes sense. Someone with a calculator, do that. This will give us V squared. Okay, we got a problem here, Houston. Okay. No, it's okay. The delta Y is going from up there to down here, so Y final minus Y initial, that's also negative. Sorry about that. That gives you a minus here too, okay? Because Y, the delta Y is always minus initial, final minus initial, this is 0, that was 945, okay? So that makes that a negative. As I said, you can't have a square that's negative, but that's where the minus comes in. Minus that minus the plus. So someone multiply those together. 2 times 9.8 times 4.4, 945. Oh, well, wait, I'll mess with the units. Meter squared per second squared. So what that number come up being? Units are meter squared per second squared. 18,522. Probably with some decimals, right? We'll leave the decimals there. Don't erase them or anything. What we've got to do that's V squared. We want to know what V is. So what do? How do we get V? Take a square root. Very good. but we take a plus or minus square root. Now we have to answer the question, what is it doing? Which way is it going? It's going minus. So we'll take the minus, throw away the plus. Okay? And what's the square root of that number you had in your calculator?
136.
V is approximately 136.1. Okay, 136. We're taking a square root of the number. We also take square root of the units. That would be meter per second. That will be a negative because it's heading downward. And let's see what they got. Negative 136 meters per second. Now, if we had used it at 941, we might come out a little bit less, but not much. Okay? They incorporated some round-off error in their calculations, so they wound up with some round-off error. Okay. Any questions on that? Do you see how to do that? Okay. I think that is the last slide. Okay. We've got about 15 minutes left. We may just go in 10. So we'll have a little time between classes. So let's get started. Or let me give you this as an option. Let me make sure I've got it here. I think it is. Since we won't have time for lab today, I can at least give you your second test if you want to have that to be working on. What do you feel about that? Yay or nay? You do want it? Okay. All right. I'll have to run down and get the copies made. So I'll be right back. So what I'm going to do is pause. Okay. Oh, let me go over this. I am recording now, yeah. Let me just remind you of things that might be helpful to you. The end of the chapter on page 53 and following is a summary, which does a pretty good job of summarizing concepts and also summarizing equations. Now, won't have all the equations here, but it does have quite a few. Then you have conceptual questions. I think these odd ones have answers in the back, maybe not all of them, but some of them do. Let me just check and see. Yeah, conceptual questions generally have odd numbers in the back. But then the more important ones are the problems. And these might be helpful in doing questions on the test as well. So any of the odds for 2.1, any of the odds between 1 and, wow, there's a whole bunch of these. 1 and 25, that's really 2.1 and 2.2. 2.3, 27 through odds 27 through 43. And 2.4, odds 45 through 53. And then they have some additional problems that don't depend on just one or the other. You can do any of the odds 55 through 71. All right. Then, motion in 2 dimensions. This is topic 3. Okay, we don't have long, but let's at least introduce it. What's that? Oh, we did too. Yeah, remember when I got stuck down there? That was a break. I said, y'all take a break. I said, don't y'all need a break? And a couple of you raised your hand and said, let's take a break. And, okay, my goodness. It was a long, way more than 10-minute break. Okay, but I am going to stop a little early just because I've got to get ready for the next class as well. Okay. So let's just go over while we're waiting for PowerPoint to come on. What will we do next time? We will have class for an hour and 30 minutes. That's from 2 to 3:30. And then we'll have the lab that went with topic 2. And it won't take you a full 2 hours, so you're going to get plenty of break time next time, Ryan. Okay. So, let's look at chapter 3. Now, we've done some of the slides on this. Remember, we did the vector slides before. So I'm only going to hit the ones that are in topic 3 here. I don't know if I have time to do any of them, but let's see. Slideshow from current slide. Okay. Now, and again, because of this, why is this starting? This is picking up where we left off last time. The previous equations, and just to remind you what those are, these are this kind of equations. Here, we talked about components of a vector, and these previous equations are valid only if theta is measured with respect to the x-axis. I think we talked about this too, so I think we did cover that. Okay. Now, a little bit more about components. The components of the legs of a right triangle whose hypotenuse are A, tells your vector A, your x component, your y component. Okay? Because x component and y component are always perpendicular to each other, then you can use Pythagorean theorem to get this. A is equal to a sub x squared plus a sub y squared. Okay? And also theta is equal to the inverse tangent of a sub y over a sub x. And they still have to find, I think we did this, didn't we? When we did the vector part? I'm pretty sure we did. I don't know why it's showing up here, and I think we did that. Well, if we didn't, I talked about it. Sometimes we'll choose to do, for instance, when we do inclined planes, we'll use our coordinate system, not the xy plane, but we'll elevate that and go from there. Okay? So we'll do that. This wasn't covered in, okay, let's see where we pick up. Didn't we talk about adding vectors algebraically? Choosing? Yeah, pretty sure we did this one too, didn't we? I don't know why it had me start at the wrong place. We did that. This starts motion in 2 dimensions. All right, here we go. In 1 dimension, we could just designate our vectors positive, negative. That gave us our directions. When we're dealing with 2 dimensions, now we have plus and minus signs are not always sufficient. In fact, they may even be detrimental, okay, because they don't fully describe the motion in more than 1 dimension. So vectors are used to more fully describe the motion. Still interested in displacement, velocity, accelerations, just like before, but now we have to do them as vectors with 2 components each, most of the time. And here's where we began here, displacement. And let's just say that's where we'll start next time, okay? So what we'll do, we'll begin right here next time with 3.1. This says 3.3. 3.1, and we'll build from here, and we'll go an hour and a half from 2 to 3:30, and then at 3:30, we'll move to the lab. We'll probably go next door here to 253. Now, if we find out it's in use, we'll go down to 259 if that's not in use. So we will have some options there, but I'll find out if I can beforehand. I may not know immediately before. Yes, sir. Huh? You can get a copy if you want to, but just don't use it because I only made enough for 1 each. Okay, thank you. Yeah, thank you. Okay, I may not ever finish grading. Come in faster than I can grade it. I got all your stuff graded, by the way. I just don't have it on Blackboard. I think I told you that. Okay, thank you. Excellent. Okay.
So I started my UAB class before this. I haven't before this class. Right. So I might be like 10 minutes later. Okay. So just let you know.
Okay, thank you. Just make sure I mark you every time you come in. Okay. I usually see you, but if you sneak in, I'll need to tell me. Okay. Goodness gracious.